Imagine whispering to a friend in a quiet room. Now imagine trying to whisper in the middle of a crowded stadium. Your voice hasn't changed, but understanding the message becomes much harder. Communication systems face the same challenge. The unwanted signals that interfere with useful information are called noise, and they fundamentally limit every wireless system. In the previous lesson, we learned that every communication system relies on a channel to carry information from a transmitter to a receiver. Unfortunately, no communication channel is perfect. As signals travel, they become weaker due to attenuation, reflect from surrounding objects, and are affected by the environment. However, there is another problem that exists even if the channel itself were ideal. Every electronic circuit, antenna, amplifier, and receiver naturally generates tiny random electrical fluctuations. At the same time, external sources such as lighting, electronic devices, and other wireless systems add additional unwanted signals. This creates a fundamental engineering challenge. If useful signals are always mixed with random unwanted signals, how can a receiver determine which information is real? To answer this question, we must understand the concept of noise. Noise is any unwanted random electrical signal that is added to the desired communication signal during transmission or reception. Unlike interference, which often comes from other intentional transmitters, noise is generally random and unpredictable. It does not carry useful information, yet it occupies the same communication system as the desired signal. Noise can originate from many sources. Thermal noise is generated by the random motion of electrons inside electronic components. Atmospheric noise comes from natural events, such as lightning. Man-made noise is produced by electrical equipment, motors, computers, and countless electronic devices. Together, these noise sources limit the ability of receivers to detect weak signals. Intuitively, imagine trying to read a handwritten letter while someone continuously spills random ink across the page. The original message is still there, but the unwanted marks make it increasingly difficult to understand. Noise affects communication systems in much the same way. Physically, consider a Wi-Fi receiver inside your laptop. The incoming RF signal arrives at the antenna, carrying useful information. However, the receiver electronics themselves generate thermal noise, while nearby wireless devices and environmental sources contribute additional unwanted signals. The receiver must separate the useful information from this constantly changing background. Mathematically, engineers model the received signal as the sum of the transmitted signal and random noise. The ratio between useful signal power and noise power, known as the signal-to-noise ratio, SNR, is one of the most important performance metrics in communication engineering. A higher SNR generally means more reliable communication. Noise influences every stage of RF system design. Receiver sensitivity, communication range, data rate, modulation schemes, coding techniques, and transmitter power all depend on how much noise is present within the system. For example, satellite communication receivers must detect signals that are only slightly stronger than the background noise. GPS receivers successfully recover extremely weak signals arriving from satellites over 20,000 kilometers away. Modern Wi-Fi and 5G systems continuously adapt their data rates according to the measured signal-to-noise ratio. At the system level, RF engineers work to minimize internal noise through careful circuit design while maximizing SNR using better antennas, low-noise amplifiers, filtering techniques, and efficient communication protocols. Noise represents one of the fundamental limits of communication systems. No matter how advanced the transmitter or receiver becomes, completely eliminating noise is impossible because some noise is generated by the laws of physics themselves. A common misconception is that increasing transmitter power can always overcome noise. While stronger signals often improve communication, excessive transmitter power may create interference, waste energy, or violate regulatory limits. Good RF design focuses on improving signal quality, reducing system noise, and using bandwidth efficiently rather than relying solely on higher power. Although noise is always present, It is only one factor that changes a transmitted signal. Signals may also become weaker, distorted, delayed, or reflected as they travel through the communication channel. In the next lesson, we will explore signal degradation and discover the many ways communication channels modify transmitted signals. In this lesson, we learned that noise is an unwanted random signal that limits the performance of every communication system. We also explored the major sources of noise, the importance of signal-to-noise ratio, and why minimizing noise is one of the primary goals of RF engineers. In the next lesson, we will explore signal degradation and discover how communication channels alter signals through attenuation, distortion, delay, and other real-world effects. If you found this useful, like the video, subscribe, and follow for the next lesson.